Um, yeah, hi everybody. Thank you, Sergio, for the introduction. And as Sergio said, no, it's a great pleasure to have Yunyao Li for IBM from IBM Research here to give the keynote of the workshop. She's very well known in the NLP community, and well, her list of accomplishments is very long. So I will simply mention that. She's filed and received of nearly 50 patents, and she's an ACM distinguished member. So these are very high-level recognitions, and we actually would need a dedicated session to go through all her accomplishments. So I will just leave it here. Let Yunyao to go to go ahead, present her work. And yeah, this is going to be mostly for us to learn about what the NLP field looks like today. So thank you again, Yunyao, for agreeing to present with us, and the floor is yours.
Yeah, thanks very much for the nice introduction, Luis, and thanks to the organizer for having me here. So today I'm going to share some lessons we have learned in taming the wild west of natural language processing. You may wonder why I give the name of wild west of NLP, right? So let me share with some initial thoughts. So what makes something almost like wild west? First of all, there is a very valuable content available, right? Almost like mining gold. And secondly, there's a lot of interest in getting that valuable information out. So if we look at the number of publications from AI, in particularly from NLP community, it's really growing in an extremely fast pace. And then with the global market, the estimate is growing around 20% for the next few years, from a few $1 billion to over $20 billion. Meanwhile, if we look at the different players in the market, there are many of them. The market is highly fragmented. There is no obvious winner in the market yet. So in other words, similar to what we have in the Wild West, there is gold in the NLP. There are many players, many fast technology up and coming, and things are moving really, really fast. So here I'm going to share some lessons we have learned and also experience we had in really taming the Wild West. Okay, so what are the challenges when we talk about NLP in the wild? There are many, many of them, but I'm going to highlight 4 of them that we have encountered over and over again. First, complexity. There are lots of complex documents, right? So for example, in this particular workshop, people are dealing with audio, and I'm going to show you example of other modalities that we need to handle for natural language processing. And the same with the problem itself can be very complex, and that impacting how do we do model building and evaluation. The second challenge is small data. So even though these days all people talk about big data, right? In reality, especially when we deploy NLP in practice, the actual label data representing the task that we care about is actually tend to be very limited. In some cases, maybe we don't even have the unlabeled data at all. So I'm going to share with you some lessons we have learned in addressing this challenge. And then the third one is for companies like IBM, right? We often build things for other people to use, but whatever we build out of box may not be good enough for individual tasks, right? So instead of building everything from scratch every single time, we can leverage what we build out of box and let people to be able to customize what we build, adapt to their domain, incorporate their domain knowledge, and support a wide spectrum of users, from AI engineers to subject matter experts. And finally, one important part people talking about these days is trusted AI, right? One big part of trusted AI is explainability. So we need to think about how do we explain the rationale behind predictions and reasoning made by the machine to experts for different persona and for different use cases. So I'm going to talk about each of the challenges and also share with you some of the work we have done in addressing those challenges. So overall, we combine a few different techniques together. One is data augmentation. How do we create data at a scale? The second is domain-specific language plus powerful primitives. So rather than build everything from scratch, end-to-end model every single time, we can build upon powerful models and then create abstractions around those models, and then build potentially a much simpler model on top of that for individual use cases. And then another approach is neurosymbolic AI. So we talk about neural models all the time, right? And then 10 years back, everything is about symbolic, right? So how do we get the best of both worlds? I'm going to share with you some of the work in my team that really combine this together to get both worlds. And finally, it's not just about machine learning, right? We also want to involve human in the loop, not just at the beginning of data collection, but at the model building, feedback, and so on. So I'm going to share with you some of the work we have done in how do we effectively enable human to work together with a machine to produce the best possible outcome. So now I'm going to talk about each challenge in a bit more detail. The first challenge is complexity. So how do we address complex documents and also address wide variety of tasks? The many things we do here, but two things I want to highlight is one, data augmentation, another, human in the loop. So document conversion, I know most of the audience probably do not deal with PDF document that much, but think of this, PDF is also a very different modality than text. So PDF is a format designed for printing, designed for human consumption. Even though to our eye, we can see all these structures, right, of title, columns, and so on, the actual representation of those information in the PDF document are very, very low level, like characters, another positions, graphic lines, and so on. So the challenge of document conversion is how do we turn those low-level features, right, using visual clues and ML algorithms to capture the high-level structure and preserve them so that we can fit to the downstream application. And in addition, just for table alone, don't ignore all the other aspects of PDF. There are many, many things in a PDF, right? You have text, you have table, you have charts, you have many other things. Just table alone, it's already very hard because a wide variety of tables. We have table with graphic line, table with visual clues only, table mixed with other things, table with complex structure, table with textual content, and so on. So imagine, how do you create a machine learning algorithm to take all this variety into account? One challenge we had when we're starting with the problem is that there's very little label data available. So one big work IBM has been working on is using automatic data generation. We create label data at scale. So previously, the benchmark data people may have a few thousand tables. Through data augmentation, we're able to create a number of data set with hundreds of tables, hundreds and thousands of tables, and this enables the possibility to apply a more sophisticated machine learning algorithm like deep neural network, right? So, but before we apply any more sophisticated learning algorithm, we first solve the data problem. Then when we have enough data, the second part is look at the problem itself. So for people working on computer vision, PDF conversion may be viewed as a object detection problem, but unlike a typical object detection problem, table has two interesting parts. One is detecting table boundary and detecting table cell. They are not disconnected. If you do object detection, maybe you identify human and you identify flower, but they don't necessarily have any constraint. But when we identify table, we know that a table must contain table cell, and table cell must be contained in table. So this allows to design this machine learning algorithm that we enforce this constraint. So while we have independent object detector detect the table boundary and table cell, we also enforce this constraint. One must occur within the other. In addition, we'll also do some clustering to look at different type of table, potential table, and do additional processing. Like for example, if we identify there's table with graphic lines, we apply a separate pipeline versus tables do not have any graphic line. So taking all the characteristics of table into consideration, we're able to do much better in terms of the table boundary detection and the cell detection. And this is reflected on public benchmark data. So you can see what we published early this year, right? What we call GT, Global Table Extraction. If you look at the numbers, it all outperform previous state of the art. And in addition, this particular work, as some of you may know, we partnered with the AI tool last year to augment the COVID-19 dataset, which initially when it was released, stripped all the table out. We added the table back through collaboration with AI tool. And then we also work with some other team within IBM to enable them to do table question answering. By understanding individual tables from PDF, we enable them to be able to do more sophisticated question answering over tables. So here's a list of publications that you can take a look if interested. One thing I want to emphasize is the following. If we look at the numbers, right, we are state of the art, but at the same time, the difference doesn't seem to be so significant. This is because based on the metrics people use for those data sets, it's very difficult to reach, beyond the state of the art because we are already almost 100%, right? So, but if we use metrics that really better reflect the downstream processing, our advantage even more obvious. I'm not going to go to a lot of details, but let me show you an example. So from this table, right, original PDF, we extracted two candidate table, both missing out some of the cells from the table. So now the question is, which one is better? I cannot say the poll, but if you can, try to answer the question, do you think A is better or B is better? I'm going to give you maybe 10 seconds to answer. Okay, so now let's look at what the benchmark data set says. From ICDAR 2013, using the metrics they have, which measure the table area and the cell adjacency, like how the cell next to each other also identified as next to each other in the actual conversion, you can see B is slightly better, right? Now, if we use the metrics used in ICDAR 2019, which measure table area, they are the same. However, if we think about how we're going to use those tables, for example, one use case is I want to be able to answer revenue for different airlines, right? In order to answer that, I need to know, like, for example, here, 1.1, it is the revenue for a airline ticket number SAVE, and it's a revenue in $1 billion for year 2028. So you can imagine if I output table B, I cannot recover any meaningful information related to these numbers because the fact those are revenues for certain year completely lost, right? While for table A, I may miss some data cells, but I can still recover pretty much the information for every single number here. So as a result, if we use the functional metrics, which if you're interested, you can look at this paper to see what it means. Table B completely fails. It returns 0. So when I talk about our table extraction significantly outperform others, we are comparing using functional metric, because this metric is really important for a large amount of downstream applications. So I think you may not necessarily working on PDF, but this applies for everything. So when we measure the performance of our model, we really need to think about how the model is used and what metrics actually represent the important use cases. So now let's move on. So even though our table extraction algorithm is state of the art, in reality is we learn from a few hundred thousands of table, right? There may be a lot, but if you think about it, the number of PDF document content table out there, what we have is really a tiny portion of the universe, right? So in order for our customers, our users to be able to adopt what we build to work data set, we also come up with a very interactive customization tool where they can load the document, and then we will automatically identify tables that we are less confident about and ask the user to say whether this is correct. If it's not correct, we also provide a way for them to quickly correct the mistakes made by the model, and then that will return to the backend to refine the model. And also we don't need them to label everything. We use what is the labeled through clustering to propagate the annotations to other similar label, and all of those will add together to refine the backend model. So typically with maybe label 10 to 20 table, you can customize the refining of the GT algorithm for your own data set. Okay, so move on to the next challenge, small data. So there actually many problems related to small data, right? What I just talked about for PDF is already a small data problem, but I'm going to share with you one particular small data problem we have been working on in the past 5-6 years. So this is related to semantic row labeling. What is semantic row labeling? On a high level, you can view it as a task that identifies shallow semantics from each individual sentence. It tells you who did what, to whom, when, where, and how. Like for example, from this sentence, we know there is the action of order, we know who placed order, what has been ordered, for whom, from where, and so on. So this is a very useful thing to be able to provide out-of-box natural language understanding for any given text. However, the challenge is that if I want to do this for other languages, we simply don't have the corresponding label data for those languages. For most of them, we don't have. But if you look at the information captured in each individual sentences, right, they're actually quite similar across different languages. No matter what language you are using, right, you always want to express the information about who did what, to whom, when, and how, right? So now the question is, how do we provide this kind of annotation for different languages at a scale? One idea we come up a few years back was through annotation projection. So this leverages the fact that a lot of data out there called bytext or parallel corpora, where you have one sentence in one language, in this case, English, and then have another sentence, which is a translation of that sentence in another language. And then we can project the annotation from the source language to the target language. So you can see here, for instance, from English subtitle, we can project the label about buyer, purchase, and item price from English to German. So the benefit is that we can generate a large amount of training data at a scale really very quickly, because all we need is the English annotation and then sentence alignment algorithm. However, there's a mistake when we just do simple projection, because there's something called a loss in translation, right? So the translation shift that lead to errors, and then there are also annotation errors from English itself. So what we did was that we created a bunch of filters to detect translation shift and block certain projections. So this way we can preserve the projections are highly precise. Of course, this is at the cost of losing some of the sentences that is actually projected correctly, but because we have a large amount of data, we can afford to lose some data so that we can bias towards precision. Then we use bootstrapping learning to improve recall. So you can think of when we have the annotation projection, we have relatively smaller amount of data than the previous what we previously had before the annotation projection. But even that, it's hundreds, at least tens of thousands of sentences that allow us to learn a model. And then we can use this model to repair any annotation projection that has been removed. We add more sentence, then we can train an even better model. So we can do this iteratively in a few iterations, and finally create a data set with both high precision and also reasonable recall. So you can look at the number here, right? For predicate and argument, using this completely automated approach, we can get pretty decent data set. So we released the data set a few years ago, and I would like to share with everyone you that we are also working on a newer version. In the newer version, we're going to have data set with higher quality and also a few other things people have been asking. And right after this particular work, we also was wondering, how do we inject some language knowledge, right? So one way is we can look at the frame mapping. So when we do the annotation projection, instead of looking at every single individual entry, we can look into, can this predicate in the target language map into this source language? In some cases, it's clearly incorrect, and then we can identify those manually and remove them. But remember, here we're not looking at each individual sentences. Instead, we're just looking at the frame mapping themselves. So we're looking at a couple of thousand of instances of the frame mapping rather than tens of thousands of actual sentences. Similarly, we can also see maybe some of the frames, like the same word in English can be mapped into two different words in another language or vice versa. In that case, we can merge them together so that we don't have too many sense in the target language that make the data even more sparse. So in general, within a few days, we're able to curate the frame mapping and create a data set with high quality. So you can see, for example, for Chinese, we reduce the number of frames significantly, and importantly, we improve the precision of the final created data much better. So this is at the cost of losing some sentence, but remember, we have a large amount of sentence to work with, right? So higher quality is more important than have lower quality but more sentences, because we want to use this data for training. Later on, we also kind of really still think about how do we inject additional language knowledge. So one idea we had is, hey, maybe instead of just using expert, because previously every single sentence was labeled by expert, right? When we have English proper bank, it was labeled by expert with years of effort. And you cannot afford to do that for all the languages in the world, because there are over 7,000 of them, right? Even for 20, it's already multi-decades effort. So what we're thinking is, can we somehow reduce the workload required by expert by being able to crowdsourcing some of the tasks? And what we initially found is, if we just give the task to the crowd, because the task, especially in difficult cases, really hard, crowd actually works worse than the machine learning model. So then what we did was we identify tasks that are easy and doable by crowd and route those to the crowd, and the rest go to expert. So what we have done is basically increase the overall performance, the overall quality of the data set by 9% point, but at the same time reduce the expert efforts by about 2/3. And we keep on pushing this because 2/3 is still a lot. Then late last year, we published another work where we actually designed a workflow. So instead of having a machine learning algorithm learn whether a task is easy, we let the workflow and the crowdsourced workers' results to decide that. So we have a filtering step and select step, and finally anything still require expert attention, go to expert. So through this step, we increase the quality of the final data by about 10 percentage points, and then reduce expert efforts by close to 90%. So it's actually very, very useful results in terms of be able to scanning labeling for this kind of data set. So again, SRL may not be something you are doing, but the message here is that we want to leverage crowd, but we need to design the workflow in a very intelligent way. Because a lot of time, if you look at today's NLP data set, a lot of time people using the crowdsourced data set as gold. And our experience, for example, from SRL shows that it's definitely not the case. So for difficult NLP tasks, untrained human can perform worse than machine learning algorithm. So we have to be very careful when we use crowd to create a data set. We really need to validate the quality before we make any kind of claim. Okay, so now move on to customizability. So as I mentioned before, right, IBM is a business-facing company. IBM Research, we help IBM build products that can serve our customers so that they can solve their own problem. So we want to take into consideration the rich domain knowledge and also support a wide spectrum of users. So when we think about the wide spectrum of users, a simplified view is we can divide them into 3 categories. The AI engineers who are comfortable at the software programming, they can develop and deploy AI models. We have data scientists who has reasonable understanding of business needs, can do data wrangling, develop AI model, and distill insights from data. And we have SMEs, subject matter experts, who really understand business needs. They can communicate business needs. They can do data labeling. They can use AI model, provide feedback. And then with some intelligent tools, they can also create reasonable AI models. So I'm going to share with you the different thread of work we have been doing. And then I will also share with you a vision of how do we tie all the different tools together into a more unified user experience. So if we think about the dimension of NLP customization, first of all, think about 4 things. Labeling efforts, how much labeling efforts required. The second is development efforts, how much effort will require to create or customize an NLP model. The third is constraint. What kind of models we can actually build? Is there any kind of limitation on what is possible through a certain method? And finally, the amount of errors. So the actual approaches can be divided further into 4 categories. The first one is rules, declarative system, where you can write the rules yourself. To do that, you don't need any labeling. It requires a lot of development efforts. It has some constraint because there's certain kind of models you cannot express in rules. And the errors is reasonable. If you put in enough efforts, you can create rule-based models with state-of-the-art performance, but it takes a lot of effort. And then we can also have some simple machine learning approach that induct rules like patterns. I'm going to show you an example. And then, we can use a conventional supervised learning approach where we have lots of label data. We also spend a lot of time, build the model, refine the parameters, tune the hyperparameters, and so on. Then you can pretty much do any kind of model using this approach, right? The error is also reasonable. And finally, I'm going to share with you some of our new work on how do we automate a lot of the model building process so that we may not necessarily reduce the labeling efforts completely, but definitely significantly reduce the development efforts. Okay, so let me first talk about the rule-based approach. So this kind of started over 10 years ago, right? From my team, we have created a system called System T. It's a declarative text understanding system for the enterprise. So the architecture looks very much like a database. So we have a declarative language that allows users to specify the semantics of extractors declaratively, and then the optimizer will decide what's the most efficient execution plan that implement the semantics, and finally a very efficient operator runtime will actually do the execution. So on the right hand side, you can see a sample extractor where basically identify very simplified person-phone relationship where it specifies, okay, find a person and a phone number within the same sentence and within 0 to 30 characters and contains certain clue words. But this only specifies the semantics. It doesn't tell you whether to find a person first or phone number first, or maybe find the clue words first for phone and phone number. It's all depending on the optimizer to decide what is most efficient way to do the execution. And we also have formally proved that this language is more expressive than cascading grammar, and also it provides a certain guarantee that we're going to find a optimized execution plan that is at least as optimal as whatever come up through cascading grammar. So by having this kind of declarative system, we kind of allow users to not worry about the execution. All they need to worry about is the semantics. And that is what we're going to leverage later on when we talk about rule learning and induction. So this is a system that we have been building, ever since I joined IBM, but doesn't mean we work on the same thing. So at the beginning, we focus on the syntactical abstraction, right? Like tokenization, part-of-speech tagging, dependent, and so on. And also some of the syntactical NLP operators like regular expression, dictionary, span operation. In recent years, however, we focus more on the semantic abstraction. How do we provide out-of-box understanding for natural language, for table, so that we can build a very simple model on top of those kind of abstraction, very simple, but very powerful for different domains. I'm actually going to show you one such particular model for compliance domain in a few slides. So this is a system that embedding over 20 IBM products, and we also published a lot of paper focused on, the design of the language, the runtime optimization, and the development tooling, and so on. So I'm going to share some of you here, and then also a lot of our new work. So for example, what I talked about earlier, right? Semantic role labeling is one way for us to provide cross-lingual semantic abstraction through System T. We developed a lot of tooling for different users. So we have full-fledged Eclipse-based IDE that allow AI engineers and data scientists to build a model from scratch using the language itself. We also have a visual IDE that allows the users to be able to develop the extractor just through all this visual composition. So the visual IDE, the expressivity is about 80% of the full language. But it also gives you the option of, for cases that you cannot express visually, you can fall back to this AQL. So for example, this is what is used in our Watson AI Ops to extract important entities like the service number, error code, and so on. Then for the second kind of customization is really through simple rule learning rule induction, pattern induction. So this is something we actually just released very recently. So the idea is that the user don't need to know a particular language. Instead, the user give us some examples, as few as two. So when the user give a couple of examples, we start to induct patterns that capture those examples. Behind the scenes, there are many multiple possible patterns. So we don't show those patterns to the user. Instead, we share examples that can help us distinguish which pattern to continue, refine, and use. So the user just give us some feedback from here. Typically, I few to a couple of dozen. And then through this iteration, we learn a better model, and the user can look at what has been extracted within the document, as well as through the output here, and to be able to give us further feedback. So if you are interested, you can look at our recent press release, which we share some of the information and also some of the papers. One thing I want to mention is we actually have a upcoming paper in Trip AI next year that help us to evaluate this kind of human loop system. Because our experience when we started working on this with the product team is that people report, ad hoc issues. We can fix those issues, but we have no idea after we fix those issues, are we doing better or worse? If we are doing better, by how much, right? So therefore, we come up with an simulation-based framework that actually simulate different kind of user model, different ways of user interact with the system, so that we can compare whether the system improve overall, and also this help us inform some of the design decisions. So this way, we're not going to be have philosophical discussions about whether we should do option A or B. Instead, we can simulate and then decide. Because in enterprise environment, we cannot necessarily push out both options and do A/B tests. Instead, we need to do this kind of things in advance at a scale. So I will be very happy later on to share more details about that paper. And then supervised learning, this is something everybody is doing, have been doing. But I want to share one interesting thing we are doing. So instead of learning a black box model, like many of our colleagues and the competitors, right? In my team, we actually have a particular work that allows to learn rules expressed in AQL, for example, what we have shown earlier. What this allows to do is now the user can come in and verify the models. So rather than the user give us all the information through label data, which typically is a very expensive and tedious process, and most of SMEs really don't enjoy that, they can come in and look at what the machine has learned and then be able to augment what the machine has learned. On the high level, we hide this structured learning task as a parameter estimation task, where we basically turn all these rules into different predicates, and then we hide a layer per predicate in the class, and then in the last layer we aggregate all the scores across actions in the sentence, and then allow us to add multiple clauses in the DNF structure that we learned. So in the end, we can surface the rules learned in a UI like this, where we can tell the user, for example, this particular rule is identified as communication because the context matches certain dictionary and the voice is passive, and the user can actually go inside to be able to look into what are the matches for the pattern. They can also decide to add and drop a predicate and play with it. One thing I want to mention is these rules, maybe to many of the audience here are not exactly easy to understand. For the people who are developing this system, they do understand. However, we are also working on an alternative version of providing explanation in a way that is even more consumable. But the point is that when we have this kind of system, And when we did a user study, we can show that user can, using this human in loop approach, to learn very good rules within half an hour that is comparable and often better than what have been learned using black box model. So it shows that the explanation of the learned rule is really effective for people who understand the concept that we shown earlier, and it greatly reduces the human labor, right? And then it also reduces the requirement on human expert, because what we find is the co-created model by engineers with less experience is actually on par with the model created by super experts. So this is a very interesting and promising direction, and I'm going to share with you in a few slides some ongoing work of bring this one step further. And finally, in the area of NLP customization, to share with you some newer work from my team on auto AI for text. So the idea is, assuming we have sufficient labeled data, we can allow the user to specify what kind of models they are looking for, right? Are they looking for models that are highly accurate, or they are looking for models that really can run super fast with reasonable runtime performance? So they can specify a bunch of constraints, and that constraint will be taken into consideration by the optimizer. And then the optimizer will automatically decide, right, what are the data pre-processing operator to use, what feature riser to use, and also combine the transformer and the estimators together, that we can perform both neural architecture search and also allows declarative pipeline composition. So in the, we do automatic selection and a model tuning. And then after this, we share what we have learned with the user, allow the user to inspect the pipeline learned, and then select the final model based on their inspection results. We provide two kinds of UI. One is low-code UI that is really, really easy to use, only take a few clicks, where you load the file, you can either choose the default experiment setting, or you can change some parameters, and then you can get the results back after waiting for some time. Like in this case, wait for 23 minutes. Then we have, a set of models coming up, and we also show you the overall number for those models, and then what are the differences, and you can dive even deeper to look into details of the difference. We also, for more advanced user, we also provide a Python interface that provide more control, that allow them to customize search space, and also allow them to actually create a customer pipeline rather than let the system explore all the possible pipeline. So our initial experiment shows that we're able to achieve state-of-the-art or better over academic benchmarks. So we have some number here. You can see we can explore, comprehensive set of pipeline and be able to produce often, state-of-the-art results or better. And then for our IBM Watson NLP production model, we can actually also help them to find a better pipeline, where we find a pipeline that have significantly less training time required with higher quality. So in other words, our initial experiment really shows this is very promising in terms of being able to significantly reduce the user efforts and also improve the quality of model generated. Finally, to put things together, right? I introduce, multiple different things. It may be a bit confusing to the user, like what to use. Our vision is something called Snooze. We want to have a system that is learning to understand text with human in the loop. That really enable this continuous feedback loop between model training and SME input, and the fact that we have different kind of models behind the scene, different techniques behind the scene, should be transparent to the user. So we are aiming to provide a unified and empowering user experience to allow all these techniques to be used intelligently without the user's awareness to solve their problem. So you can think about the user experience I showed earlier for the pattern induction. Right now, it's learn patterns behind the scene. We're actually working on have similar user experience to learn more sophisticated model and for more type of tasks such as classification. So I hope, in a couple of years, I can share more on how we provide this more unified user experience. And finally, explainability. So one big question when it comes to explainability is who need to know what and when. We have a recent paper I encourage you to check out. I don't want to go into a lot of details, but let me show you some examples. Like, for example, I already explained Heidel, right, which provides explainability for data scientists. But this is for data scientists. The user need to understand, the meaning of different predicates. They need to know F1 measure, precision record. They need to have some knowledge. But at the same time, what we want to do is actually provide a simpler way for the final user. Because when we provide a model, we also want to enable the final user to understand what we have. So we have an ensembled model that you can think of. We can combine this white box model with human loop with a black box model. So that allows us to produce natural language explanation for most, if not all, the predictions. So let me share with you an example. Like, for example, in our production, we have this system. These are all out-of-domain performance. Therefore, it may not look as high as it typically is. But you can see, right, using black box model, we can have very high recall but lower precision for out-of-domain performance. And then when we do this white box training, we can have high precision but lower recall. But overall, it's actually better than what manually created. However, if we ensemble them together, right, with two different approach, one approach is kind of, we want to maximize the overall performance, especially focus on precision, right? So we can explain about 90% of the cases. In another case, we want to really emphasize on recall, right? We want to have maximum recall as much as possible. Then we can explain 50% of the use cases. However, one important thing to think about is, in either case, the average performance in terms of F1 measure is better than what is provided by black box model or the manually created model. But at the same time, we really benefit from full explainability. So I promise I'm going to show you, how do we use this natural language understanding to build a product, right? So this is a very simplified view of that. So we can load a contract, and then for every contract, we can explain, do the classification, and also be able to allow the user to provide some feedback. How we build this, we first take each of these elements, think of a sentence. We turn those sentence into a semantic NLP primitives that are based on semantic role labeling and a few other things. This will tell us, what is the action, performer of action, tense, and so on. Then a legal expert can work with AI engineers to come up with this kind of legal domain logical expression that allows us to do the classification. And then finally, based on this, we can say, okay, if a sentence contains a business transaction with tense of future and is positive, then classify this as obligation for purchaser. So this is a completely transparent process. And this allows us to be able to use systems like Model Lens to be able to look into the errors and identify the resources of the errors and then be able to fix them. So I will not have time to go into those. And finally, I want to briefly mention, for people interested in explainability for NLP, I encourage you to check out our work on that summarized a lot of the literatures in this direction. You can look at can go to our website and also go to our latest KDD tutorial. Okay, in summary, the key to tame the Wild West of NLP are really, first, we need to understand why we need to build this NLP model, right? We want to solve a business problem, not just because we want to build a model. Then we can think about how this model will be used and evaluated, right? Because in some cases, for example, recall is important. Some cases, precision is important. Some cases, explainability is important. We really need to understand what kind of, like how it will be used and evaluated. Then we will identify what kind of models we need and what's the best way to build it. So I think this is a very simplistic way to think about the whole process, but it's also very important. Don't start with, I want to build a model. You really need to understand why, how, then you can think about what to build. Thank you very much. This is the end of my talk, and I want to thank all my team members and my colleagues around the globe in IBM research. And I really miss our team in this beautiful Amazon lab. And I welcome the audience, if you have the chance, come to visit our lab.